Video 52 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is frequency-dependent polarizability. In chapter 4, we had an expression for electric dipole moment or a component of the electric dipole moment in the presence of a static and homogeneous external field, where we expanded it in the permanent moment and an induced moment. Now, in this chapter, we are going to look at not a static and homogeneous external electromagnetic field, but we are looking at radiation. So we are looking at coherent polychromatic electromagnetic radiation, and we're making Doppler approximation, which means that the electric field is oscillating with time, but it's constant, again, uniform over the extent of the molecule. So therefore, now we have a dipole moment which is perturbed by an oscillating electric field. And therefore, we will generalize this expansion from chapter 4 to be, again, the permanent dipole moment plus an induced dipole moment, but now induced dipole moment by this time-dependent external field. And again, the induced dipole moment will be the product of a polarizability tensor times the components of the external electric field. But now the electric field is time dependent, but not space dependent. So we have here the amplitude times the oscillation, which we express with the cosine of the frequency times the time. And since we are looking at polychromatic electromagnetic radiation, we have this integral here over all possible frequencies in this pulse of polychromatic electromagnetic radiation. Now, since the field is oscillating, or we might have different frequencies, then maybe it's not so surprising that, of course, also the value of the polarizability, or the components of the polarizability tensor, to be more precise, also depend on the frequencies. And we use here this notation for indicating these frequencies, where the frequency behind the semicolon are the frequencies of the fields which are applied, and the frequency in front of the semicolon is the frequency with which the induced dipole moment here is going to oscillate. So that's a linear term. We also had quadratic terms and cubic terms before. Here, just write the quadratic term up, which includes the first hyperpolarizability. And we have two time-dependent oscillating electric fields, whereas the first one I let oscillate with a frequency omega 1 and the second one with a frequency omega 2. Since we are also, both those fields are polychromatic, so we have two integrations, one over all possible values of omega 1 and one of all possible values of omega 2 again. And here again, you can see these are the two frequencies coming from the two fields, omega 1 and omega 2. And that is sort of the frequency with which this contribution to the induced dipole moment is oscillating. Our expansion here, our generalization of the expansion to the time-dependent case, where we have the integral from 0 to infinity for the frequencies. Now, as before, for the time-independent case, the polarizability, which is the frequency-dependent or dynamic electric dipole polarizability, is a tensor, and we can define then by summing the diagonal elements divided by 3, we can define the isotropic value of this frequency-dependent electric dipole polarizability. Now, the polarizability, in particular this frequency-dependent polarizability, is the molecular property, the property of molecules, which give rise to the fact that material have an refractive index. So it's the molecular property underneath or underlying the refractive index of a macroscopic sample, a macroscopic material with a number density n. And one has derived relations between the two of them. And I'll show you here the relation for nonpolar molecules. The reason for that is because if you have polar molecules, you will also have a contribution to the macroscopic polarization to the microscopic property from the alignment of their dipole moments, and we're not interested in this right now. So here's the expression for nonpolar molecules, which means without a permanent electric dipole moment. So the refractive index as a function of the frequency is this square root of the expression where we have here the polarizability and the number density, so the number of molecules per volume. And being a square root, we can approximate this in this form, 1 plus, so the 1 plus the molecular frequency-dependent dipole polarizability of the molecules making up this material, and here the number density then. Which means that the dispersion of the refractive index arises to the frequency dependence of this polarizability. And now we want to derive expressions for quantum mechanical expressions for the frequency-dependent polarizability, and being this a time-dependent phenomenon, we are going to use our time-dependent response theory. We have and cos, which means we look at the expectation value of the electric dipole moment operator here, the time-dependent expectation value of the electric dipole moment. And we know that we can expand this in, of course, the expectation value, the time-independent expectation value of the dipole moment operator, meaning the permanent dipole moment, plus an integral over response functions with the appropriate operators and times the corresponding components of the field. So what we have to do now is we have to figure out what are the operators which we have here. I mean, the first one, of course, we have the first operator in the response function, because that's the operator of the property which expectation value you're looking at. And in the case of, in our case here, this is the dipole moment operator, of course. Now we have to figure out what is the perturbation Hamiltonian and therefore our perturbation operator. Now, as we just saw in the section before and also in chapter 2.9, if we apply A, the Doppler approximation or the long wavelength approximation, and then the length gauge, then the time-dependent electric field enters the Hamiltonian via the scalar potential. So we have the scalar potential. And if we now, as said, looked at the periodic but spatially uniform electric field, meaning the Doppler approximation, then we can write our perturbation Hamiltonian this way. Here we have our time-dependent electric field, now only time-dependent because it's spatially uniform. And here we have a component of the perturbation operator, which of course then being coming from the scalar potential is going to be the dipole moment operator again. Now writing out the expression which we had for, which we just had derived in the last section, for the time-dependent but spatially uniform electric field, we can write it up as either cosine omega t or omega 1t, or using Euler relation, we can write it up in this form. And since we're looking again at a polychromatic pulse, we integrate all frequencies. Now, as you hopefully remember from chapter 3 and response theory, we need to write our perturbation Hamiltonians in terms of a Fourier transformation, which we can do again here because we have two exponential terms. So we can use this one of them, this one, rewrite it to extend the integration here from 0 to minus infinity, as I've done here, which comes from making use of this term. So we left with this one, which really looks like, I mean, it's a Fourier transformation of our electric field in Fourier components here, which are here the amplitude divided by 2. So therefore we can identify now our perturbation Hamiltonian and the components of the field, and can insert this now in the expression which we had for the expansion of the expectation value of some operator in response functions with the line as the frequent chapter 3, which basically looked at this here. So we have the time-dependent expectation value of our operator, in our case, because we're looking at dipole moment, the dipole moment operator, as being the permanent dipole moment or the expectation value with the unperturbed wave functions, and then a series of corrections to that, which are linear, quadratic, cubic in the field, and the linear one has the linear response function. And as this being the operator of our expectation layer, that's the first operator in the linear response function, and the second operator is our perturbation operator, which was minus the corresponding component of the dipole moment operator, and here we have our field. Now, in order to compare to the pen, we have to rewrite it also here again. So we reduce the integration now again to 0 to infinity, which means the first half the integration from minus infinity to 0, we're going to rewrite as being again from 0 to infinity, which means we generate the second term again, and so we can also rewrite it as cosine. Now, comparison with the expression, the expansion of the dipole moment before, we can then realize that the component of the frequency-dependent polarizability is given as this response function. It's minus the response function with two dipole moment operators or the component of the dipole moment operators which correspond to which component of the frequency-dependent polarizability we are looking at. Now, in order to calculate this, now we can of course use the matrix representation of our response function as it was derived in chapter 3.11, I think. But we also can look at the spectral representation of the response function, meaning write it up as a sum of states expression with here the exact excited states of our system, where we have two terms, this one, that one. And now what I do in the final step here is to bring this expression on a common denominator, because here we have h bar omega 1 plus the ground state energy minus the excited state energy, whereas in the second term we have minus h bar omega 1. So if I bring it on a common denominator, which is then the excitation energy or the energy difference from the excited state minus the ground state squared minus h bar squared times the frequency squared. And that gives us an extra energy difference here in the numerator. And it actually shows, which is difficult to see in the first part, in this part up here, it shows that the frequency-dependent polarizability actually depends on the square of the frequency and not linear on the frequency. So it's actually depending on well, it's 1 over the square of the frequency, which one means one can write it up as an expansion in the frequency squared, frequency to the fourth power, and so forth. If we would now consider the frequency independent case, meaning setting the frequency to 0, which is called the static polarizability, then this expression will, particularly in this form here, then we easily go back to the expression which we had derived previously in chapter 4 for the static polarizability by just using second order perturbation theory. So this linear response theory approach and the static and the second order perturbation theory approach give us the same results if we go for resolution for expanding it in the exact excited states of the system.